All right, hello everyone. Let me just first talk about course recommendations. So real quick, I think many of you guys have gotten back to me, rising juniors and rising seniors, that whether you want to take AP Stats or BC Calc, I'm still missing information from a few of you. So just to let you know, vast majority of you are choosing AP Stats, which is great. That's fine. So I'm going to treat that like default. So if you have not gotten back to me by Friday, I'll just put you in for AP Stats. But just also understand that you can always change your mind. I just need to have something down on paper or on Infinite Campus for next year. So if you change your mind or you decide you want to do something else, you can always do course change later on. Okay. All right. Any questions there? Okay. So let's give a preview as to what I would like for us to do today. We have some additional notes that we didn't quite get to on Monday. So I want to spend some time going over that. We're going to kind of discover that relationship of position, velocity, acceleration, but going from the other perspective, where we're starting at the acceleration level, finding antiderivative to get to velocity, finding antiderivative to get to position, and also just a little bit of definition of displacement and distance from an integral perspective. So we'll do that. Most of our class will probably be spent on this. And then I want us to spend a little bit of time on calculator. Just going to start with the really basics. We just need to be able to find derivative and integral, slope at a point, and area under a curve using calculator. So this will be something that will be tested on the test. So some parts of the test, you can just plug in and find the value, just seeing if you can go through the features on the calculator. And other parts are where you got to work it out by hand. You got to show me the work. So I'm going to show that so both types of problems are going to show up on the test. Okay. I'm going to be working mainly with these two types, 84 or 36 Pro. I'll show you how to do in either calculator. If you have the Inspire or TI-89, then I don't have those directions spelled out here, but if you do a quick Google search, YouTube search, you should be able to find directions on how to find these items that we're doing here. And if you still feel like that's not sufficient, or you want me to walk through it with you, feel free to reach out and to me, and we can find a time to work together and get you comfortable with your specific calculator. Okay, so we'll do that second. A couple of things that I also included under today's link is this formula sheet. Okay, so this formula sheet, I will include this as an additional page on your test. So if you're here taking the test, you'll get your test, and I'll give you these formulas, and I'll go over some of these. And also, we'll include this if you're taking it on Teams, virtual. I'll also have this at the back as the last page, so you can have it referenced and have it printed out. I'm still, if you printed out yesterday, I added a few things. I may add a few more things here. So, feel free. If there's additional things that you want to place, you can, definitely print it out and keep adding to it, either more details or more information or more. There's a lot of different variations of first theorem. So I want to start to kind of help us understand how this is so flexible. We can do a lot of variations of these and help use this to solve a lot of different types of problems. Okay, so I have derivative rules here that we've been introduced to. Sorry, up here. Integral rules that we've been introduced to, and then these two theorems that kind of show that relationship between integrals and also between integrals and derivatives. Okay, so I'll refer back to this when we are going into our additional notes. And if we have time, I don't think we will, but if we do, then we can start some of the chapter 4 test review. But more, what's going to happen, I think we're going to start that tomorrow, and we'll have Thursday do test review 1, Friday do test review 2, and Monday do test review 3, and then I'll give you guys an idea as to what to expect on the test, and some problems to focus on, other problems to ignore, and then test will be Tuesday. Okay, so all right, let's start with some definitions here. Displacement is how far you are from where you started. So the notation for displacement is just the definite integral of velocity from A to B, okay, where v of t is the velocity function. So displacement is just the integral of velocity. Okay. Distance is the total amount a particle has traveled. So distance is the integral from A to B, but the difference here is that we have an absolute value around the velocity function. And what we're doing here is we're treating every forward and backward motion as a positive value. Okay. The thing that's unique here is there's the absolute value bar, but it's important where you place the absolute value bar. Okay, it's going to go just around the velocity function. It's not going to go over the entire expression, and that is where I see some mistakes on past tests, where the location of the absolute value bar is incorrect, or plug it into the calculator wrong, and then that will also produce the wrong value. So I want to make sure, this is what I see some students do, though. These are not the same thing. Okay, if you put the absolute value bar outside the integral, that's something else. Right? That's not something that we're going to be doing. So what this is doing is it's taking all the positive and negative regions, it's combining them, and then if the value ends up being negative at the end, it's going to convert that to be a positive. And we're not going to be using that feature. Okay, there's not be an instance where we're going to be using this type of problem. Yes.
Wait, so like Mr. Yang, the absolute value outside of the integral, that would just be like, for example, it would be 8. So with this curve, it would be 11, but like absolute value 11. But instead of that, it would be like 13.
So the distinction here is, this may not, right. So what this is going to do is this is going to, it's going to total all the values up, like 10 minus 2 plus 3, which is 11, and then absolute value of 11, right? And then, but if we do it the way we're supposed to, then that means we're going to treat each subinterval as a positive value, so it'll be 15. 10 plus 2 plus 3 is 15. Right, so we're more concerned about this. This is not something that we're going to be using. Okay, so we're either going to be treating each subinterval as a positive, or we want to keep track of positive and negatives, but we're not going to total everything up and then convert it to be positive that happens to be negative. We're not going to do that. Okay, so I've gone through the definition, so I'll go through an example, and hopefully that will help clarify any remaining questions that you still have. So suppose a graph represents an object's velocity function. The number inside each region represents the area of that region. Let me talk first about, I want you to visualize what this object is doing with this velocity function, and then I'll talk about the number. So let's say this object is moving along the x-axis, and these represent the time. So y-axis is velocity, x-axis is time. So I want you to visualize it as I'm describing this scenario. So this object is going to start at time t equals 1, t equals a, and it's going to start moving to the right. So above is moving right, below is moving left. It'll start moving to the right. It's going to cover some significant time interval. And we see this object is going to pick up velocity, right? So pick up velocity, it's going to pick up, it's going to move at the fastest at this point. It's going to start slowing down, but it's still moving to the right. And all this while it's picking up distance, right? It's covering ground as it's moving to the right, okay? But it's moving to the right, picks up speed, hits its maximum velocity, but then it's going to start slowing down, but still moves to the right, and then it's going to do what? Okay, it's going to stop, right? Stop, turn around, and start moving left. So it starts moving left. It's not going to pick up a lot of speed, but definitely it's going to reach highest speed in the left direction, and then it's going to slow down, but still moves left, but then it's going to stop. Turn around again and moves to the right. Moves to the right, picks up speed, not as much as before, but enough to still gain some distance, and then it's going to stop. Okay. So you can visualize this object moving left and right. It's going to move right longer and faster and cover more ground than it does moving left. And then the area, the number inside is going to represent the area. So basically, if we accumulate this velocity over this amount of time, then that's going to tell us 10 means over this time period, it's going to cover 10 units to the right. This 2 means that it's going to stop, it's going to go backwards 2 units, stops, covers 3 units to the right. Okay, so be able to look at this and just be able to visualize this object going back and forth, moving at specific velocity, stopping, turning around, and covering a certain amount of distance. Okay, so I want you to have that picture in your head. Now, based on the graph, the object's displacement is just the integral of the function from a to b. So for displacement, we are just concerned about what is the net gain of this object, meaning after everything is said and done, how far is this object from its starting point? Okay, so we know it's going to move 10 units to the right. It's going to go backwards 2 units, so we got to make sure we keep track of that. So 10 minus 2, and it's going to go 3 units to the right. So he travels 10 units right, 2 units back, 3 units forward. So in the end, he's going to have made progress of 11 units to the right. So after the dust settles, this object is going to be 11 units further to the right than where it was at the beginning. Okay, that's displacement. Okay. Any questions there? All right, now total distance, we're still going to use the numbers, but we're going to use the numbers a little differently. We're going to put absolute value around v of t. Which means that we're going to treat every distance, every value as a positive. So he's going to move 10 units to the right. He's going to move 2 units to the left, but we're still going to consider that as a positive value. And then 3 units to the right. So total distance, if we treat everything as positive, this object's total distance is going to be 15. Okay. And another analogy is imagining if you're driving in the car and you're going back and forth, right? If you're going back and forth, your progress may be hampered by the fact that you're moving back and forth, and that's going to affect your displacement. But your odometer is going to read 15, right? If you go forwards 10 miles, 2 miles backwards, it's still going to count everything as positive. So the odometer reading, think of that as the same scenario as how we would find total distance. Okay, any questions there? Okay, we're going to explore this a little bit further and also introduce another related concept on the back page. Okay, but want to start to have that idea introduced before we get to it on the next page. Okay, so we also are going to revisit position, velocity, and acceleration. First semester, we understood that position, velocity, and acceleration is just that relationship between function f prime and f double prime, right? We know how to get from function to first derivative to second derivative. And that's exactly that relationship between position, velocity, and acceleration. We're just using different variables in a different context. So position, we usually use x of t. Velocity, we usually use v of t. And acceleration, we usually use a of t. But we're able to move our way down from one function to the next using derivative, right? And we defined velocity as the rate of change of position. So rate of change of position, that's really slope of position. And we define acceleration as the rate of change of velocity. So rate of change, slope, right? Slope of velocity lead us to information about acceleration. Okay. And so it stands to reason that we can go the other direction, right? If I can find the derivative this way, that means antiderivative will allow me to start acceleration and move my way up the chain. Acceleration to velocity will be antiderivative step. Velocity to position will be another antiderivative step. So that's exactly what we can represent using antiderivative. If I'm starting at my acceleration level, I can take the integral of acceleration. So if I accumulate acceleration over a time period, I'm going to result in information about velocity. Okay. If I start at velocity, if I accumulate velocity over time, that's going to give me displacement information. Right? If I travel 60 miles per hour for 5 hours, that information, right, it's going to lead me to 300. That value tells me information about displacement, about position. Okay. All right. First semester review here. Increasing speed and decreasing speed, we can find that by comparing signs between velocity and acceleration. If velocity and acceleration have the same signs, then we know speed is increasing. If velocity and acceleration have opposite signs, then speed is going to be decreasing. So here's an example there, right? Acceleration and velocity have the same signs, either both positive or both negative. We are expecting increasing speed. If one is positive and the other is negative, then decreasing speed. Okay. Good so far? Okay. Hey, before we move on to the next page, we're going to be revisiting a velocity graph on the next page. But the difference is that we're going to be finding the areas on our own. These are given to us because these are not nice shapes, and we don't have the function, so we can't find the antiderivative. But on the next page, we're going to see nice geometric shapes, and we're going to find the areas on our own. But we're going to be accumulating them just like how we did here. Okay. Okay, next page. I'm going to keep going back and forth between notations of f prime and velocity because they are kind of one and the same, but sometimes it's easier to visualize something in terms of f prime versus velocity. So I'll just kind of interchange between them depending on the scenario I'm trying to demonstrate. So the direction says that our derivative graph is shown above. Use this graph to answer the following. Find the x-coordinate of relative extrema. So if this is the derivative graph and I want to find relative max or relative min, I have to understand that that this is not the shape of the original graph, right? We can find out information about the shape or behavior of the original graph by labeling parts of our derivative graph. We know anything above the x-axis is going to translate to a positive slope on the original graph. Anything below the x-axis is going to translate to be a negative slope. Anything on the x-axis is going to be slope 0. So I'm going to just create a slope sign line and try to get a picture as to what the original graph looks like. My critical point is at 1. And between 0 and 1, negative slope. Between 1 and 4, we see positive and negative slope, but then all this is just variations of positive slope, right? Some steeper than others, but they're all positive slope. So looking at these arrows here, we can kind of visualize how the slope is moving, right? The graph is going to be falling, relative min, rise again. So we know for part A, relative extrema, relative min at x equals 1. Because f prime changes from negative to positive. Part B, find the x-coordinates of points of inflection. So we learned first semester, right, that if we're looking at the derivative graph, the way we find points of inflection is a little bit different. We don't look for x-intercept, we look for peaks and valleys, right? So peaks and valleys are going to be locations of our point of inflection on the original graph, right? This is not what points of inflection looks like on the original graph, but this is where it's located if we're looking at the derivative graph. So we know there's a point of inflection there, and if I want to just gather a bit more information in terms of concavity, I can look at the slope, right? Slope of my derivative graph is going to translate to concave up on the original graph. Negative slope translates to concave down. So there we see a change in concavity here. That's the point of inflection. Because f double prime changes signs. Okay. I'm going to introduce a new topic, subtopic here, where we're going to be involving displacement, but we're going to be looking at finding specific locations of the original graph based off of the derivative. So I'm going to go back to thinking in terms of velocity and thinking in terms of this object on a number line, just moving back and forth. And we're going to try to place where this object is at specific time periods. Okay, I'm going to start there, hopefully get us to visualize it without the calculus getting in the way. And then after we can visualize it, we'll talk about how to put it into calculus notation, and then so that when you have something abstract, you can always go back to that visual picture that we're going to start with. Okay. So I'm going to go back to this being a velocity graph. Okay, so this object is moving left, stops at 1, turns around, moves to the right, gathers momentum, gathers velocity, and then it's going to stop again. And the area inside in these regions will indicate how much and in what direction this object is going to travel. Okay, But these are all nice geometric shapes. We're going to find these areas on our own. Okay, so first off, I'm going to start off with this is a triangle, right? 1/2 base times height. Base is 1, height is 2. 1/2 1 times 2, that gives me 1, but it's below the x-axis, so it's just going to help me indicate that I'm going to put -1. So we know that between 0 and 1 second, this object is going to move 1 unit to the left. Okay. There are different ways that we can visualize this, but I think that's the easiest way, where just imagine this object moving back and forth on the x-axis. Okay, are we good with that visualization? Okay, so we know from 1 to 4, he's going to start moving to the right, and it's going to pick up quite a lot of speed here, and it's for a larger time interval, so we know it's going to make a lot more progress moving right than left. Okay, so I'm going to start with this large triangle, and we can subdivide it later. But this triangle here, 1/2 base times height as well. My base, that's a base length of 3, right? 4 minus 1 is 3. And then the height of 4. So 1/2, 3 times 4. 12 divided by 2, that's a total value of 6. I'm not gonna put that 6 in here because I'm gonna subdivide that, because we're gonna need to subdivide it for part C. So I know this full area is 6, but I'm going to kind of subdivide this triangle a bit more so I can have more detailed sub areas of these regions. Now I got a triangle here, I got a triangle here, but there's a trapezoid here. We have a formula for trapezoid, but I think we can avoid it if we just find these two areas, subtract from 6, and we can find that missing trapezoid, right? Okay, let's start here. 1/2 base times height. This is 1/2 1 times 2. So that's going to give me an area of 1. Positive, because it's above the x-axis. And this is also a triangle here. 1/2 base times height, 1/2 1 times 4. That's an area of 2. We know this large triangle is an area of 6. I have 1 and 2 here, so this missing part must be what? 3. Okay. All right. I want us to just do the visual portions of this without any of the calculus getting in the way. Okay. So let me start with the scenario. Time is going to pass, and as time passes, we're going to know how far and in which direction this object is going to travel. Okay, and we're going to use that knowledge, and you're going to tell me where the object is going to be at certain time periods. Okay, so let's say initially the object is going to start off at 1 on the number line. Okay, so I'm just going to draw this. So no calculus yet. I just want us to be able to visualize this before we can go further. So we're going to start here. So the argument inside these position is time. Okay. So we know that he starts here. He starts at location 1 on a number line. He's either moving backwards and forwards. So after 1 second, where is this object going to be given this information?
0.
0, because this indicates that he's going to travel 1 unit to the left. So if I'm starting here, if I move 1 unit to the left, I'm going to end up at 0. So I'm going to say x of 1 is equal to 0. Okay, good so far? All right, x of 2. Again, I'm always going to go to my starting point. I'm going to start here. Where is my object going to be looking at these numbers after 2 seconds?
Back at 1.
Back at 1, right? I'm starting at 1. I'm going backwards 1 unit, but I'm going forwards 1 unit as well. So I'm going to be back at 1. So I'm here. I go backwards. I go forwards. I'm back at 1. Okay. All right. x of 3, again, I'm going to start at 1. I go backwards 1 unit, forwards 1 unit, forwards 3 units. Where is my object going to be after 3 seconds?
Be at 4.
Okay. Okay. So backwards 1 unit, forwards 1 unit, forwards 3 units. Yeah, 4. Okay. X of 4. Okay, this is not the same thing, right? This is talking about location, this is talking about time. So where is this object going to be 4 seconds into its travel? Backwards 1 unit, forwards 1 unit, forwards 3 units, forwards 2 units. Where's that going to be? That's 6, right? Backwards 1, forwards 3, forwards 2. 1 minus 1 plus 1 plus 3 plus 2 equals 6. Okay, so we're doing this without any calculus notations. We're just visualizing based off of where the object starts. We're just moving it back and forth depending on our velocity information or the area under the velocity graph. Okay, are we good with that? Okay, good. So now let me introduce you to the notation that we want to be comfortable with. Okay, so this is the first theorem of calculus. This says that if I take the integral of my function, it'll bring me up to my antiderivative. And a variation of this is using velocity, right? This is basically displacement here, saying that if I take the integral of velocity, it'll give me my position B minus position A, and that will give me my displacement. If I rearrange it, this equation, I can think of it as this thing, this equation that will be helpful as we think about PVA. Any final position I'm looking for is my initial position plus displacement, right? So that's exactly what we've been doing here, right? We always started at 1 because that's our initial position, and this displacement is the sum of the moves that we did after our starting point. All right. So if I want to find the final position, I have to be able to know where I'm starting, and I move accordingly based off of that information. Right. So another thing to keep in mind is there's a distinction between displacement and position. Okay. Another analogy is, if you know that a friend is going on a road trip and you're calling that friend up and you're asking them how much progress that friend made in that course of that day. And let's say your friend tells you, made a lot of progress to travel 200 miles, right? So that would be information about displacement. But if they just tell you that they traveled 200 miles, you really have no idea where they are on the map, right? It could be all over anywhere in the US or anywhere in the world. But then if that friend tells you that it's 200 miles from Chicago, they have a better sense of where he is or how much progress he made. So that's the distinction. Displacement is progress, but then final position is where physically is that object after that progress. So we're going to achieve this using integral notation. Okay, we're going to get all these numbers again, but I'm going to use integral notation to help get us there. So going back to C here, and this is the formula we're going to be using here. Any position I'm looking for, any location I'm looking for, I'm going to have a starting location. This is always going to be given to us. Okay, we always have a starting point, and then we want to know how much progress we made from that starting point. So, final position is equal to initial position, and just think of initial position as the given. Okay, it may not always be 0. but it's always going to be some anchor point to start off with. And then displacement is kind of, think of it as the progress that you've made in travel. So again, let's say we start off at x of 0 equals 1. That's the given. Right? So if I want to find x of 1, I'm going to say my starting position, starting location, plus the displacement between 0 and 1. So we know our starting position is 1. And then between 0 and 1, we know we're going to travel backwards 1 unit. So we're going to end up at 0. Right? Just like how we were doing it with our number line, but using integral and calculus notation. If I want to find x of 2, I'm going to start at position 1, and I'm going to total that distance from 0 to 2. So it's going to be 1, and then between 0 and 2, we know it's negative 1 plus 1. So backwards 1 unit, forwards 1 unit. And we're back to where we came from, right? And that's what we were discovering here. X of 3. I start at location 1, and then I just figure my progress over the course of that time period. I start at 1, but then I'm going to total my region here. So I go backwards 1, I go forwards 1, I go forwards another 3 units. And I end up at 4, location 4, on the number line. X of 4, same idea, start at 0, start at time 0. But I need to bridge this gap between 0 and 4, so I'm going to find my displacements. And just like what we did, we just total those numbers up, right? Negative 1 plus 1 plus 3 plus 2. We're going to end up at location 6. Okay, so I want us to be comfortable with these notations. Okay, but I started us off with a visual anchor, so you can always picture what's going on based off of these notations. Okay, a few more things here. Okay. Part D says state the absolute extrema. So that just means find the highest and lowest point. So that just means on the number line, what's the least value and what's the furthest left and furthest right this object's going to achieve. And we can see that the smallest number is 0, so that we know that's absolute min. Absolute max, obviously 6. Okay. Parts E and F is saying find total distance from 0 to 4. I'm going to put this down here because I want us to see that distinction between position, total distance, and displacement. So part E says find the total distance. So total distance between 0 and 4. So we talked about total distance involving absolute value. So total distance, I'm going to say integral from 0 to 4. Those are the 2 time values they gave us. absolute value of v of t. And we talked about how total distance, we're just adding all the values inside our region, treating everything as positive. So what's the total distance that this object is going to travel between 0 and 4?
7.
Yep, 1 plus 1 plus 3 plus 2, 7. Okay. Part F is displacement. From 0 to 4, so integral of from 0 to 4 of v of t dt, our notation has no absolute value here. Displacement is where we look at the same numbers, but we keep track of our negatives and positives. So if I add all this up, what's my displacement going to be?
6. Oh, 5.
Okay, yeah. So if we're going from 1 to 4, it'll be 6, right? But we're including that -1 there, so those will cancel out. We get 5. Okay. So I want to just go ahead and make sure that we're clear on these distinctions. I want you guys to see that distinction between final position, which is really location of this object, okay, versus total distance and displacement. Okay, so look at how we find each of these and how they are different, but then also related, right? Displacement is just what is the net gain of this object. Total distance is, okay, I'm looking at my travel, but I'm treating everything as a positive value. But location requires us to anchor with the starting point. We're going to have displacement involved in location, but after we figure out our net gain, we have to be able to know where we're starting from so that we can figure out where we're going to end up physically on the graph or on the number line. And the reason why I want to bring that up is I see a lot of students making mistakes with total distance and displacement because they want to add that initial position, right? We don't add an initial position to total distance and displacement because we're not concerned about the location. We're just concerned about the amount of travel that this object is going to undergo. So I see a lot of students, they want to add a position, they want to add a starting point to distance and displacement, but we don't do that, right? Now, displacement is a part of position, of location, but it's only a portion of it. And I see students getting confused or thrown off between these three categories. So, okay, any questions between those? Okay. Great. Okay, we'll revisit this as we do our test review, but at least we have some foundation to work off of. Okay, let's look at some calculator features. So the two most important thing I want to be able to go over is finding slope, finding the derivative at a point, and then finding area under a curve, definite integral displacement. Okay. If you have, I'm going to be using 84 and 36 Pro. I'll show one example on one. I'll move to the, so depending on which one you have, or if you have both, you can practice them on both. Again, if you have other calculators and if you're having trouble finding it online, or if you have trouble getting what I want us to be able to do, then reach out to me, and I can always try to find a way to find time to work with you. All right, so first thing is make sure that you're in radian mode, but ultimately radian mode is only going to impact you if you have trig. But just to be safe, just always in radian mode, and we don't have to worry about it later on. So just if you go to mode, just double check that you're in radian mode. Radian mode should be the one that's highlighted. All right, so I'll start with the graphing calculator, and I'll move to the 36 Pro. So what we're going to do is I want to kind of talk about what this calculator can do for us. So imagine I want to find f prime of 7 for this function. Right? Normally, by hand, you would go through power rule, right? Maybe a little chain rule here, but you go through power rule, chain rule, find the derivative, plug in 7, and that will get you to a number, and that number tells you how steep this point is on this graph, right? But we're going to make the calculator do the work for us now. So first thing we're going to do is we're going to go to math 8. So if you look on the calculator here, there's a math button in that first column there. So do math. And we're going to scroll. You don't have to scroll down every time. You can just hit 8. But I want to show you what that looks like. It's going to be n deriv. Okay, n deriv. So if you do math 8, it'll bring you to this derivative notation. Okay. And you're going to put x into that space there. It's always d over dx, even if your problem on paper is a different variable like theta or t or y. Don't make calculator switch variables. Okay? Always use x. It's gonna complain if you use other variables. So just always give it x. Okay. Next, we're going to plug in the function. So the expression that we want to evaluate is this 2x cubed minus 5x squared plus root at 7x. So 2x cubed minus 5x squared plus square root of 7x. I don't know if it's not enough light, it's hard to see. Okay, but then when you scroll to the right, there's still that space there. So we need to fill in that empty space with 7 because we're asking the calculator to find the slope of this graph at 7. So what we're going to get back in return is a number, and that number is going to translate to the slope of this function, 224. So it's going to be a very, very steep slope. We can skip a lot of the steps. So that's something that I want us to be aware of. Okay, now moving on to 36 Pro, we can also do the same thing. But if you look, do you see that there's a d over dx there? It's in blue. It's right below second. And we're going to do second natural log, and that's going to bring us to that d over dx. Okay, notice it's going to look exactly like what we did on the graphing calculator, and we just enter everything in as you see. So you can put that function in, 2x cubed minus 5x squared plus 7x. Now, your x is next to the 4. So your variable x is next to the 4. If you tap it more than once, you're going to hit other variables, but we're always using x. Make sure you scroll to the right, because we have to. It can't find the derivative function for us, okay? But it can find the derivative at a point, so we always have to insert a number. Okay. Any questions about where the buttons are or getting to what I got there? Okay, the second thing I want to be able to show you is that we can also find the area under a graph. We can do the definite integral as well. So let me show the directions on the next page. But instead of math 8, we're going to go to math 9. So there's that f and integral feature that's on your calculator. So if you do math, you can hit 9 directly, but I'm going to scroll down to show you what that looks like. F and integral here. You're going to see that math print notation is going to look exactly like the notation that we've been using on paper. So you're just going to put your lower bound here, upper bound here, the expression, and dx. Now, I made a mistake here. I had -2, and -2 is not going to work with the square root, so sorry about that. So let's make it go from 2 to 11. Type in your expression, 2x cubed. And then don't forget, you got to fill in that dx at the end here, that space, that's always dx. That just means I'm finding the derivative, sorry, the integral with respect to my independent variable x. And it's going to give us displacement, area related, assuming everything is above the x-axis. Okay. Any questions with entering that in? Okay. All right, 36 Pro, we can do the same thing as well. Do you see how right below the d over dx you have that integral notation? So we're going to get to that button there. So do second e, and you're going to enter everything like how we did before: lower bound, upper bound. Okay, any questions? Anybody have trouble getting to certain buttons? Okay, last thing I want to show you is we can also do absolute value. Okay, so we'll put absolute value around our expression so we can find the total distance. So we're still going to go to math 9, but to find that absolute value, you're going to go to math number ABS. So let me show you what that looks like. So I'm going to do 3x squared plus, but first I'll do math 9. I'm going to go from lower bound from 0 to 5. But before I enter in my function, I'm going to select that absolute value feature. So go to math. So math is right below the second button there, math. But instead of scrolling down under math, you're going to go to number and then see ABS. So number ABS. And that's going to pull up the absolute value bars. Then you can put your expression inside of it. And then make sure you complete with a dx. Now, just to let you know, sometimes absolute value in the calculator just takes a little bit longer. It may take sometimes up to 15 seconds for it to process, so just be patient. Just to let you know that sometimes it may take a little longer. Okay, now on your 36 Pro, you're going to still select your integral notation. I'm going to go from 0 to 5. And then to get that absolute value bars to show up, you're going to see that math button there. It's going to be very similar how we move around this. So do math, scroll over to number, and then ABS. So I have it all spelled out on the direction sheet, so you don't have to memorize it, just be able to practice with it. Okay, absolute value bar shows up. We enter the expression inside of it. And we should get the same answer. Total distance. Absolute value of our velocity. Okay. Any questions? Okay, there's more things that we need to be able to do, but those are the biggest things. And then the other things are graphing related that we can maybe get to over the course of these next few days. All right. Thanks, everyone. Hope you guys have a great day. See you tomorrow.